Chapter 19. So we're going to be talking about thermodynamics, but basically we will be talking about whether a process is spontaneous or not, and we will be looking at something called entropy and also free energy. These are the new terms that you build on top of what you learn in Chem 1. In Chem 1, we learned about enthalpy. So we'll have a little bit of a review of material from Chem 1 here, just a little bit. So the first law of thermodynamics tells us that energy cannot be created or destroyed. So all it does is change from one form to another form. Okay. So and also you have your total energy of the universe. It doesn't change. You don't create it, right? So all it does is that you add up the system and you add up the energy of the surrounding. You get the total of the universe, and it will add up to zero because it's just saying that it's not created or destroyed. You're just changing from one form to another, transferring from the system to the surrounding and surrounding to the system. Okay. Some review stuff here. We talk about heat and work a lot for Chem 1. So if you remember, heat is Q, work is W, and you put heat and work together, you get your energy, okay? And over here, delta E, you remember, it's a state function, internal energy. So when something is a state function, you take basically the products minus the reactants, or the final state minus the initial state. Because when you see a delta sign here, it means the change. So when we talk change, we always take the final state, whatever the final energy state is, or whatever energy we're talking about, minus the initial value, and you'll get the delta E here, okay? And they say delta E here can be calculated using the formula Q plus W, which Q is heat, W is work. And if you don't remember the formula for heat and work, these are the values for Chem 1. Q equals to MCS delta T, so I'll just explain what these values mean here. Heat equals to some amount here, usually it's in mass, and sometimes it's in moles, and then CS here is your heat capacity, a specific heat capacity, so it'll be like something like joules per grams, and then Celsius, or maybe Kelvin. Sometimes it's joules per moles. Kelvin, it really depends on the value they give you. But they can come in different forms for the CS for the unit. So I guess I can write down the units here. So CS unit, sometimes it's joules per grams Celsius. Sometimes it's joules per moles Kelvin. So depending on the unit of your CS, you put grams for this part, Celsius for this part. If you get this unit for CS, then you put not joules, you put moles here, and then you put kelvins there, just to match the unit. So you have to see which unit you use based on the CS units that are provided in the question. Now for calculation of work here, you take minus P, negative P delta V. So P here is your pressure. You'll be using ATM, okay? And your volume here will be in liter, the change in volume. So when you see the change in volume is final minus initial as well. So when you get ATM liter here, there's a conversion between ATM liter and joules. It's the same unit there. So, but if you ever have to convert, I will be providing that value for you, or you can look it up on the tables if it's not an exam, okay? If you need more reviews on this stuff here, I do have the notes from Chem 1 in PowerPoint as well. Feel free to take a look at them. If you have questions when you look at that, you don't really understand some stuff, let me know and I can go over them with you as well, okay?
Can you just say what the delta V units were again, where work is equal?
Oh yeah, I'll write it out here. So this one here will be in ATM, and this one here will be in liter. So that's
okay, thank you.
Minus pressure. Whatever the pressure they gave you, you take negative of it, and then the volume will be like final minus initial, and you use liter, because ATM liter can convert to joule. Okay? All right. That was a very good question. So hopefully you guys saw the units here. These are all just Chem 1 review, so it's good to know. If you don't remember, feel free to look at my notes from Chem 1 as well. All right, so they also talk about energy tax. Well, basically, you know, processes aren't efficient. You always lose energy here and there. So what happens is if you have multiple steps, every step you do, you lose some energy as heat form. You know, that's why it's not efficient. So if you have like a one-step process, you lose less energy, the process will be more efficient. So that's like review stuff from Chem 1. We don't have to worry too much about it. But what we really want to focus on in this chapter is talking about whether the processes are spontaneous or not. So what does spontaneous or not mean? It means that if a reaction is spontaneous, it can happen without any help. It will just happen on its own. Like it just wants to do it. Okay, so how we can do that is we determine the chemical potential of the system before and after the reaction. So if a system has less chemical potential than like at the end, it's thermodynamically favorable. So we'll talk about how to judge if something's spontaneous or not. There's multiple ways to do that. But that's what we're going to focus on, okay? Now, keep in mind, a process that's spontaneous is not going to be fast, or we don't even know if it's going to be fast or slow, to be honest. We just know if it's spontaneous, yes, it will go. If it's non-spontaneous, no, it's just going to sit there and stare back at you and do nothing, okay? But we don't know if it's going to be fast or slow. Fast or slow has to do with kinetics, which was a chapter we did earlier in the semester. Now we're just going to talk about, can this reaction happen on its own or can it not? If it doesn't happen on its own, it's considered non-spontaneous. So let's take a look a little bit more about spontaneous or not reactions. Now, so one easy example to just imagine this, not talking about chemicals yet. If you have something that's really heavy, the heavy thing, for you to lift up the heavy thing, you have to put energy in, right? But spontaneously, the heavy thing, if it's up in the air, it's going to want to fall down on its own. So that's how you know which direction is spontaneous. And you kind of like an idea, they always tell you when something is a high position, the potential energy is high. When it falls down to the floor, the potential energy is a lot lower, 0. So that's the idea there. We're going to look at the potential. As for it to be spontaneous, the chemical potential has to go from high down to low. That's how you make it spontaneous, okay? So if you have some salt sitting in a beaker and you pour water in it, that thing is spontaneous, going to want to dissolve. Salt will want to go. So, you know, just kind of saying that, is it going to happen or is it just going to sit there and look at you? So we have to look at the chemical potential, basically. Now, another thing about being spontaneous or not, if it is spontaneous in one direction, it is non-spontaneous in the other direction. Okay, so it only goes in one direction. There's no reversibility right here. Okay, any spontaneous process is irreversible. So basically, if you have a really nice brand new car, if you sit it there and do nothing after, well, it might take quite a few years, but if you do nothing to the car, it will over time rust and just, you know, not look that pretty anymore. So especially in Florida here, the cars probably rust a little faster. Or people who drive around in the snow areas and they have salt on the roads a lot, that will cause rusting to go faster. So if you just sat the car there spontaneously over time, although not a short time, probably a pretty long time, that's why they say spontaneous doesn't mean fast. Spontaneous means it will happen on its own without any help, okay? So your car will be shiny and brand new, really nice. Spontaneously, if you don't do anything to it, it can turn to be a rusty old car that's probably falling apart. Now, if you had a rusty old car that's falling apart, if you just set it there, will it spontaneously turn into that car? It is not going to be able to do that. That's why we say if it's spontaneous in one direction, it will be non-spontaneous in the other direction. Okay? So just to remind you again, thermodynamics here, we're going to talk about spontaneous or not. It doesn't have to do with how fast or how slow anything is, okay? Now, one interesting tidbit here is that graphite is actually more stable than diamond. So conversion of diamond to graphite is actually spontaneous, but obviously it's super slow. We're not going to be able to see your diamond ring turn into a pencil lead. Okay? All right. So let's talk a little bit more about spontaneous processes. So to do that, we have to start bringing back the term enthalpy. So let's do a little bit of review on enthalpy. Enthalpy has to do with endo-exothermic stuff. So we'll go a little bit over that. And then we'll talk about entropy as well. And then we'll combine those two parts together, okay? So we want, spontaneous processes. When they happen, it's because at the end, the energy for the system is low because they released the energy away into the surrounding, okay? So anything that's exothermic, do you remember what exo and endothermic are? So maybe we'll do a little review right here. So let's go ahead and talk about endo and exothermic, and then we'll come back here so you can see how exothermic can be favorable for spontaneous and endothermic is not favorable, but it can still happen, okay? Let's go back over here. So let's do a little bit of review about how to tell something is exo endothermic. Let me change my pen color. Okay. All right. So we are going to say, well, here's my delta H. Remember, delta H is enthalpy. And when we talk about delta H means it's, whenever I say delta, it means final H minus initial H, or the product H minus the reactant H, okay? But overall, if something is delta H of a positive value, it means it's endothermic. Okay, so how is something going to be showing a positive sign? So that means if you had a bank account, okay, and your money is the currency here, like energy, and how can you, what sign will you see for it to show as positive in your bank account statement? When you see something that's positive, means you put money in your bank account, right? So if you do that, for something to be positive, that means at the beginning, your balance was pretty low, and then you put some money in and your balance increased up high, so it went up that way. So we can put this in here like a bank account. So this is what it looks like if you had reactant that was low enthalpy, and then you have product that's higher enthalpy because you put in energy into the system. Okay, so this is my, I guess the H scale here. So low going to high, and this is how you can tell. So remember, positive here means energy has to be put in, some sort of, for it to go up. Okay, now this is called endothermic. So the way I remember is endo is kind of like sounds like indoors inside, so it's going in. And then it's positive bank account change. That means you have to go put money in, like on payday when you get paid. Okay, now another indication of an endothermic process is sometimes they'll say the flask feels cooler if the reaction flask feels cooler than before. So if you were to do a reaction in that, say you were holding a test tube, and as you notice when the reaction happened, you feel like your test tube is getting cooler. So when you feel something that's getting cooler, it's because it's an endothermic process happening. Okay, so now if it's an endothermic process that's happening, what's happening is the reaction needs some energy. So where is the energy going to come from? The energy is going to come from the solution molecules, the solvent molecules around the reaction. So whatever the reaction, if it's in liquid, because it's in a test tube, it's sucking the energy from the liquid portion to go into the reaction. That's why the flask feels cooler. All right, so that's how you can tell something's endothermic. Now, if it's exothermic, it's going to be the exact opposite. So exothermic is going to be a negative sign, and we call it exothermic. So if we have like a scale for energy here, trying to see the energy here. So this is the unit of H here. And then you have, it has to go down instead of going up. So it's going to go down. So when your bank account balance shows a negative transaction, it's because you spent the money, because the money was going out of your account. Okay, so this is going to be reactant, that was high energy, and then product, that's low energy. Now, in this case here, you're releasing, energy is exiting, so exothermic will be a little easier to remember. And the reaction flask here feels warmer. So if you had like a fire going, fire is basically combustion process. So the reaction is combustion, and you stand around the fire, you feel the heat. So it's the same idea as basically the reaction flask feels warm. If you did a reaction, the reaction was releasing heat, you would be able to feel it, but when you touch the flask, it felt cooler, hotter. Okay, so let's do a little bit of practice. So this is endo and exothermic, okay? So leave some space here for this side of question, because now we're doing endo exothermic. After I explain the entropy part, we'll also determine entropy signs for the same set of questions here, okay? So leave a little bit of space so you can write the S part as well. I'm just gonna show you the delta H part for now. So let's do determination of endothermic or exothermic. Okay, now the first one, the formation of dew on the grass blades in the morning. So that's a little, you know, like in the morning when it's a little cooler at night, and then you wake up, there's like little water droplets on your grass. So that's the dew on the grass blades, okay? How does that happen? What kind of process is that? How does the water appear on a glass blade? So it really was basically overnight, because it was a little cold, the water vapor in the air has now turned to water in liquid phase, and it got stuck on the grass. Okay, so it's really a phase change here, agree? All right, so we went from gas to liquid. Now, do you know the energy states for gas versus liquid? Gas is the highest energy, right? And then liquid is the middle, and solid is always the lowest. So in this case here, you actually will see, if you were drawing the energy scale up, gas would be on the top, liquid would be on the bottom here. Okay, and what are we doing the process of? We're doing gas going to liquid. It's coming down. Okay, because it's coming down, my delta H is exothermic. Everyone good? All right. Now, here's another one. The evaporation of sweat. I don't know why I didn't leave a space between my evaporation and off, but this is evaporation of sweat. So what process is this? So when you sweat, you feel cooler when the sweat dries off. That's the way our body is trying to cool ourselves off. So in this case here, your sweat is evaporating. So what is the phase change of evaporation? So we'll just call sweat water for now, okay? So it was sweat and water and some salts. And then it's gonna sweat and evaporate and turn to gas. Agreed. So essentially, it's the opposite of what we just saw. So if I had to draw a picture here, I know gas is higher energy than liquid, right? So I'm going from liquid to gas here. It's going up. So my delta H is endothermic, or a positive sign. Everyone following so far? So this is still a review material, but it's very important that we understand this part, because without this part, you'll have a hard time determining spontaneous or not later on. Okay, so make sure to review if you can't remember it. And we're also going over it here, so we're doing a little bit of practice. All right, the next one I want to ask is the freezing of water. So freezing of water is what phase to what phase? It's gonna go from liquid phase to ice, which is solid phase. So if you were to draw a picture out, liquid is higher energy than solid. So it's going from liquid to solid, it's coming down. So the freezing of water is actually coming down, so it's exothermic. All right, let's do some more. Maybe now we'll do the melting of ice. So it's the opposite, right? So the melting of ice. Ice is solid. It's going to melt and turn to liquid. So that means I have solid and I have liquid. It's going up. So delta H here is endothermic. Okay? All right. So, and then let's try another one. Another popular example is dry ice subliming. So what's sublimation process? So dry ice is carbon dioxide, right? So it's CO2 solid, and it sublimes and it goes CO2 gas. Now carbon dioxide can actually turn to liquid, but not in our atmospheric pressure. If you look at the phase diagram of carbon dioxide, the liquid phase does not exist until you go to higher atmospheric pressure. So it doesn't happen at 1 atm. That's why we see carbon dioxide go straight from solid to gas in our everyday situation here. All right, so when it goes from solid to gas, what sign do you think this is? So I'll draw solid is on the bottom, gas is on the top, it's going up. So this one, delta H, is going to be endothermic. Well, run out of space. MIC, okay? And then it's positive sign. All right, so that's endo-exothermic here. So what's interesting is here, I gave you examples that involves phase changes here. So one quick shortcut I want you to remember. When it involves a phase change, my delta H and my delta S signs are identical. Okay, so just remember that for now. I'll write it out in a second and we'll explain why. Because we'll talk about entropy. The entropy for gas is still higher than liquid. Liquid is higher than solid. So literally the pattern for the delta H and the delta S will be the same. And so if it's a phase change, your delta H sign and delta S signs are going to be identical. Okay? So so that's that part. That was just a phase change. So let's talk a little bit about endo-exothermic, and we'll talk about combination and why we have to look at entropy as well, okay? We'll come back to entropy. Okay, so it says here, spontaneous process is higher energy, higher enthalpy to lower enthalpy. So most of them exothermic. So exothermic is like basically you're starting off on a basically already favorable. If some process is exothermic, most likely it's going to be spontaneous. Okay, it's going to be spontaneous. But there are endothermic reactions that still can happen that still are spontaneous. So we say exothermic makes it good because it releases the energy. So that's what we know is spontaneous. But how is an endothermic that needs you to put in an energy still can happen spontaneously? Well, it depends on something else because we're looking at the combination of enthalpy and entropy together. So there are some processes that are endothermic, but they generate a lot of disorder or entropy. So the entropy term here overcomes the little positive net energy here that you need. So overall, it's still going to be spontaneous. Okay, so they gave you an example down here. They said, melting of ice is endothermic process. So we just looked at that, right? It says here, melting we determined was endothermic. So we already said, if something is negative sign exothermic, it's favorable for being spontaneous, but endothermic is not favorable, but it still happens. So when does ice melt? Well, only when it's warm enough. If it's cold, if it's in the freezer, ice is not going to melt. So it depends on the temperature here. So we'll be talking about temperature effect on the entropy term in a little bit as well. So it says here, when the solid melts, the particles have more freedom of movement. So that generates the entropy, okay? So ice can still melt, but only at higher temperatures. We'll talk about the temperature portion later on when we consider more entropy stuff. So as a reminder, enthalpy is delta H is delta E plus P delta V here, okay? That was a formula we learned in Chem 1. And then we have entropy change. So when you say delta here, remember it's always final minus initial. That means we're doing products minus reactants, okay? We have to look at both parts. We have to look at enthalpy and we have to look at entropy. So we just looked at some endo-exothermic here for enthalpy. So here's a little bit more description for enthalpy change, okay? So delta H are usually going to be big numbers. So we use kilojoules per moles, okay? Now, the stronger the bonds, the more stable the molecules. That means it's going to be lower energy, okay? Something that's more stable, something that has stronger bonds will be lower energy. So maybe we should write that down. Like if you were to draw the line, it would be on the, like on a graph, it would be on the lower spot, okay? It says here, a reaction is generally exothermic if the bonds and product are stronger than the bonds and reactants. So we did a bunch of calculations like this, where you looked at the reaction, you decided what bonds that were broken, what bonds that were formed. You also decided the energy for each part, but basically you're looking at products minus reactants. And if overall you're losing energy, you're releasing it out to the environment, your delta H is negative here. Okay, so that's just the idea. And then the opposite is for endothermic, where you need to put energy in for the process to happen. So basically, this case here, the reactant is going to be a lower energy. Okay, so, and then it says here, enthalpy change is favorable for exothermic reaction. We already said the enthalpy change portion, if it's exothermic, it sets it up for it to be spontaneous, a high possibility for it spontaneous. But if it's endothermic, it's not favorable to be spontaneous, but it can still happen depending on how the entropy changes. So change the page. So talking about entropy here. Entropy is basically talking about disorder, the randomness, okay? The more disorder it can have, the higher the entropy it is. So when you want to talk about delta S here, you take final minus initial. Again, it's like products minus reactants again. So when you have delta S positive for your system, that sets it up to be favorable, okay? So if the S is really, really positive and your H was a little bit positive, so it can overcome it. Now, in this case here, the rate changes in entropy when you take a look at stuff. So products are in more random state. So what's more random? Gas is the most random state, and then you go down to liquid and then solid. So that means if you have like, you know, products that are like, let's say you have liquid going to gas, then your entropy went up because liquid has less disorder than gas, okay? And then it says here, if you have a lot of product molecules, like how many moles compared to the reactants. So the more number of products, number of molecules, the more arrangements, different possibility of arrangement it can get. So the more disorder it can have. That's why it increases the entropy of your system. And if you increase the temperature, it gives them a lot more energy to run around. So that also increases the entropy. Now, when you take solid and you dissolve it, it turns into a lot of pieces of ions. So that also is an increase in entropy. So they're just giving you some examples here, okay? And we'll also work on them. So in this case here, we were saying exothermic was favorable, endothermic was not favorable. But when you have delta S is positive, the change is favorable for it to be spontaneous. When delta S is negative, the change will not be favorable for it to be spontaneous. Okay, now you gotta always remember we're talking products minus reactants when we want to look at changes. So speaking about the phase change here, right? I'm talking about state change. So we say that, you know, solid is kind of, doesn't move as much, and then gas is free to run around. So when you go from solid to gas, your entropy is going to increase. So you can actually see it on this other next graph here as well. Basically the same idea. Solid going to liquid going to gas, going higher and higher entropy. Same idea with going higher and higher enthalpy. So that's why, because of this, whatever we determine for our delta H here, the delta S is exactly the same sign. Okay, so I'm gonna write a note here to find delta S. So it will say phase changes have same signs for delta S and delta H. Okay, so we were to look for delta S for the first, delta S, not H, for the first part A here. So we say, what is the delta S sign? So we're going to do delta S positive or negative as well. For the formation of dew on a grass blades, if we know it's gas going to liquid, the delta S sign here is the same. It's also negative for the reaction, the process. And then say evaporation of sweat, well, delta H is positive, right? So that means delta S is also positive. Now this is only for phase changes, okay? If you see a phase change, you just go straight like that, no, it's the same sign. So you save a lot of time trying to determine it. I mean, you could draw it out again, but it's the same answer. Okay, freezing of water. We determined it was exothermic here, so that means the delta S here is going to be negative. Melting of ice. We determined that this was endothermic, it was positive sign, so your delta S is positive. And then you do dry ice subliming. We said it was positive endothermic process, so delta S here is also positive. So we're talking delta S of the system, delta H of the system, because the system is the reaction right now, the phase change. Okay, so now this was just phase change examples. Now there are other cases where you don't have a phase change and you have to consider other stuff, right? So let's go ahead and work on those kind of problems to determine if it's delta S that's positive or delta S of negative, okay? So you guys ready for me to change page? Let me know if you are not. I'm just gonna write some other questions so we can work on delta S determination. we want to predict delta S system, if it's positive or negative. Okay, the system here is basically the reaction and the process we're referring to. Why do I say system? Because later on you'll see there's a system component and there's a surrounding component. System plus surrounding adds to the universe. Whatever's not in a system is considered the surrounding, and add both parts together, you get the universe. Okay? I'll write it out later too, but let's focus on just the system for now. Part 8, water vapor condensing. Okay, B, separation of oil and vinegar dressing. C, dissolving sugar in tea. D, D here is a chemical reaction, so I'll go ahead and write it out. 2 PbO2 solid turns to 2 PbO. Sorry, that's a B. Let me rewrite it. Plus O2 gas. E is another reaction. 2 NH3 gas goes to N2 gas. Plus 3 H2 gas. F is Ag plus Cl negative Aq. Aqueous forms and turns into AgCl solid. And then we'll do G, the boiling of water. Okay, so give you some time to write these out and then we'll work on them together. But if you already wrote them, go ahead and start determining the signs if you can, okay? Okay, I'm gonna go ahead and do start with part A. So with part A here, they're saying water vapor condensing. So condensation is a process of gas turning to liquid. There's a phase change. So this one here, delta S, is coming down, so it's negative. Okay. Let's see the next one. Separation of oil and vinegar. So when you buy oil and vinegar dressing, or actually if you make it, the oil and vinegar do not want to mix. You have to stir it so it'll mix together, right? When you mix it up, that's when the disorder is high because it's mixed up. But when they separate, they're really neatly organized. One side is oil, one side is vinegar. So in this case here, your disorder is actually getting less disorder because it's organizing itself. One side is oil, one side is vinegar. So it's going to be, again, it's a negative sign because it's getting more ordered. Now, if you dissolve sugar in tea, what do you think the sign should be? There was big pieces of sugar, and then when you put it in tea, it breaks apart into sugar molecules flanked by the tea. So there's a lot of sugar molecules now instead of one big piece of sugar cube. So in that case, the disorder should increase because there's a lot of molecules floating around now. So it should be positive. Okay, now on part D here, you can take a look and say, well, here I have 2 pieces of solid And then I make it turn into 2 things of solid and 1 thing of gas. And then remember I said if we talked about like number of mole products versus reactants, we have 3 here versus 2 in the beginning. And on top of that, from just 2 solid, you're turning into 2 solid and a gas. So this order here is increasing. So your delta S here should be positive. Okay, let me know if you have questions. Okay, now another example here for part E is 2 moles of gas turning to 1 mole of gas plus 3 moles of gas. So 2 moles of gas turning to 4 moles of gas. So in this case, you're definitely going up in this order because now you have double the amount of gas moles. So this is going to be positive as well. And then you have aqueous and aqueous, 2 pieces combining to be 1. So in this case here, it's getting less disorder because there was 2 and now there's only 1. So delta S here should be negative. Boiling of water is a phase change. So it's going from liquid to gas. So delta S here is going to be a positive sign. Is everyone okay with the positive and negative for the delta S system? So the enthalpy portion is reviewed from Chem 1. So now they're introducing to you delta S, how to determine positive or negative, okay? Let's see. I think we're good. Okay, let's go. So we were covering the first law of thermodynamics. It says energy cannot be created or destroyed, right? So let's go to the second law of thermodynamics where we start seeing how, this is just a system portion. Now I want to show you there's actually a surrounding portion. Everyone go with this? I'm going to go ahead and show you guys slides, okay? So we're going to go to slide number 22 here. So slide number 22 tells us what the second law is. It says that the total entropy of the universe, so delta S universe, must be positive for a process to be spontaneous. So delta S universe is comprised of the system, which we just learned how to look at signs for the system. And we also have to look at the surrounding, okay? So we'll have to look at the surrounding and the system. And if you put the surrounding and the system together, you will get the universe. So basically, if I drew a little pie chart, like, call this big circle the universe, and then one part of it is a system, and the rest of it is the surrounding. Okay, it's just saying like these 2 parts make the whole universe. Whatever is not in the system is considered the surrounding. So let's take a look here. A lot of words here. I'm just going to go ahead and write out the formulas. Well, we'll write out this formula here. And then we'll talk about how to get the formula for delta S surrounding. So we just figured out how to do the system by checking the signs, right? You can actually, there's actually a little number, a calculation formula for this. So I'll write it out for you. So let's go over, I guess we'll go to the next page, okay? So I can put them both on the same page. So we were saying we need the delta S universe. So this is the second law. Delta S universe, okay, good. This has to be positive, so bigger than 0 for it to be spontaneous. Okay, and then we also said that we know the formula delta S universe equals to delta S system plus delta S surrounding, right? So we already learned about the system part just now. Let's take a look at the surrounding. So the surrounding here, they said you can actually calculate delta S surrounding by saying mine is negative heat of the system. It's really hard to calculate in the surrounding because it's like everything else. So we always try to find a term that refers back to the system. So the surrounding will always receive the heat loss from the system, that's why we just put the negative sign. So if the heat was being received, whatever the system surrounding it always have opposite sign, but basically in this negative sign here, okay? So negative Q, heat of the system over temperature. Now this temperature is in unit of Kelvin. Okay? Now, if you remember from Chem 1, at constant pressure, heat is interchangeable with enthalpy. So I'll write it out. I'll just write the H first, okay? It's the same exact thing. You can either look at the heat or the enthalpy. It's the exact same thing. So I will write a little clause here why that's the same. So from Chem 1, maybe I'll write it on the top here. At constant pressure, which the pressure isn't changing, we're at 1 atm here usually. Delta H is the same as Q. All right, so that's why we say that's the same thing. So the formula to get delta S's surrounding is actually to look at the heat of the system. Whatever the opposite change of heat for the system, that's why we put a negative sign, because system is surrounding our opposite. And you have to look at the temperature term here. And this is now going to help us explain why temperature is important to determine how things are spontaneous or not, okay? So, so to do this here, to see how big of an impact the temperature is, I want to do a really quick analogy here. So can you give me an example of someone who is really rich and famous that you would like to hear come talk to us, like give a speech or, you know, something at SBC? So we can go see, you know, if there was no COVID, and we could all gather in big gatherings. Let's say if that was possible. So in the past, I've had many ideas of people they want to hear. Like some people want to hear Oprah talk. Some people say Bill Gates. And then one time I had someone say Mariah Carey. And another time someone said the Kardashians. That was funny. So who do you guys want to think about to imagine coming to SBC? Any ideas here today? Who's BTS? I must be too old. Okay, so whoever it is, you imagine who you want it to be, okay? Because obviously I'm too old compared to you guys. I don't know who your famous people are anymore. But just imagine someone like that. So maybe we'll stick with someone like Bill Gates for now, okay? It's a boy band. Oh, okay. That's why I don't know it. What? Okay, I'm gonna have to Google them. All right. All right, anyway, so we'll pretend they're coming to SBC and you're gonna be like a fangirl, a fanboy, whatever, okay? So we're going to totally listen to them. Oh, maybe it's a famous musician. They're coming to SBC to perform for us, okay? Well, just imagine it, okay? And just escape this little thing for a little bit. So they're gonna come to SBC and perform. And after a great concert, they're gonna leave. And you know, you're still like hanging around in the venue, so you didn't see them leave yet. But as they were leaving, they were walking away and they see a huge stack of money, okay? So like, let's pretend like is this big enough of a stack? Just make, yeah, like this big a stack. Like, let's make it, what's the biggest dollar bills that they have? 100 is pretty common, right? So like, let's say you have a big stack of dollar bills like this thick, okay? And it's $100 bills and this big stack of $100 bills. So how much money do you think that is? Like, I think that's a lot. I don't know how many that would be. I've never seen a dollar bill that thick, okay? So that's a lot of money, right? Agree? Everyone agreed? So they're gonna walk out of the building, wherever they were performing, and I'm going to see that big, gigantic stack of $100 bills. Okay, so whoever you are imagining coming to SBC, I would imagine, you know, because they're rich and famous, that thick stack of money to them, they're like, oh, look, it's a stack of money. And they're like, okay. They're probably like, hey, telling their assistants or somebody, can you guys go like get the money and make sure someone finds like whoever's looking for it, whoever dropped it, you know, gets returned back to them. Okay, because you know why they don't feel so much of an impact? If you see this much money, it's like winning the lottery, right? For them, they already won the lottery 10 times over because they're so rich and famous. Their bank account is way bigger than this one stack of money here. Agreed? So adding this one stack of money into their bank account that's already super gigantic big, it's not really going to make a big change. So it's not that big of an impact to them. Agreed? So someone who is rich and famous with a gigantic bank account, if you see a stack of money like that, it's not really going to make a big change. Okay? But then they left the parking lot and they, you know, did whatever they had to do to return the money. So let's say that didn't happen and you walked out into the parking lot first. So there you are, just, you know, just got to be in an awesome concert, a performance, or listen to a really good speech, motivational speech. And then you see this big stack of money right there in the parking lot. Now, the question is, what should you do? Okay, so the right thing to do is to return the money, okay, to look for the person who lost it and give it back to them. But so you have this big stack of money. Now compare this big stack of $100 bills and compare to the size of your bank account. If that stack of money here compared to your bank account, is that going to make a big change in your bank account balance? Is it going to make a dramatic difference to you? It does. Okay, but remember, the right thing is to always look for a return to owner thing. It's not going to be finders keepers, okay? Don't do that. Anyway, the reason why we say this is your existing amount of money in the bank account is going to determine how much a little change is going to be. So if you have a big bank account, a little bit of change is not going to do anything to it. If you have a small bank account with a little bit of money, any amount of change is going to be a drastic amount. It's going to make a big difference. Okay, so in this case here, we can go back over here. So we'll think of temperature as the bank account size. Okay, if you have a big temperature, a big bank account, and you put a little bit of heat in, it's not going to make much of a difference. You're like, it's just a little bit of change in heat. We're okay. Now, if you had a really small temperature in Kelvin, and then you put that change in, even if the change is not so big, it's like, oh my gosh, what a big difference it makes. So that's what the idea is here. If you have a high temperature, the change in heat here is not going to make much of a change in the surrounding. But if you have a low temperature, any small change amount of heat here is going to highly impact the delta S of the surrounding number here. So basically the surrounding delta S can be really big or small depending on how high the temperature is to begin with. Okay? So with that example, now we want to go into an example here. Okay, so let's take a look at a picture here. I'm going to draw it out with like a little graph phase. So let's say I have a system. I'm going to draw it out here. So I have, I'm going to do a little side graph here. I have liquid going to solid. Here's an example, liquid going to solid example. So my delta S here would be negative, right? Coming down. So this is my system. Write down the system. It's a negative sign, so that's that part. So that's my delta S system. Okay, and then because the delta S system is negative here, it's kind of like saying liquid is going to go to solid. So what's an example? Maybe like ice, like water freezing to ice, right? That's an example. When does water freeze? Just a question here. Do you guys know when water can freeze? Does water freeze when it's hot or water freeze when it's cold? It freezes when it's cold, right? So that means this thing can only be, this situation here can only be spontaneous when you have a low temperature. And let me explain how we can see that, okay? So we know this one's negative here. Now, let's say we look at the low temperature conditions now. At a low temperature, because we talked about water freezing, right? We know it's low temperature. Now, the heat exchange. So how do we know there's a heat exchange? Well, you know, we know this is because delta S is negative here, delta H was also negative. It was an exothermic process. And then because it's exothermic, it gave out heat, right? It was the heat was out of the system, right? So you have a Q, and then you take the Q, the heat was received, calculated surrounding the opposite sign. And then the heat was released out. And then depending on what the T is, it makes a big impact. At the low temperature, the heat that was released has a really big impact, okay? So heat exchange of system and surrounding makes a big impact. On delta S surrounding. Agree? Because at this point, at low temp, the T is really small. Whatever the heat that was released from the exothermic process is going to make a big difference on the delta S surrounding because the T here is so small. So the delta S surrounding, we know it's going to be a really positive, really big positive value here. Right? Because we said it was releasing, so the delta H was negative. So negative on negative is going to make it positive. And we know it's going to be a small temperature here, so the surrounding is going to be a really big positive answer. Okay? So I'm going to draw the big positive here. Oh, really, really big. So this one here is delta S surrounding. So this is at low temps scenario, okay? So overall, oh yeah, let me write down the delta S system we said was negative. So basically, if you combine this term and that term, so this is just negative 2 boxes, this is going up. So basically, your overall universe is still going to be adding up to this amount. So it's still positive, okay? So overall, delta S universe is positive at low, so this is low temp. Okay, just an example here, at low temp. So water spontaneously freezes at low temps. Okay, so let's take a look and see if we did the same thing. Why does water not freeze at higher temperature? Okay, the reason it doesn't freeze, we'll draw it out in a picture down here below. So that was a low temp. Here we know water freezes at low temp. Now we want to do the same scenario here, but now we change it to high temp, okay? I mean, you already know the answer. I'm just using that example to help explain this system and surrounding thing. So we know that the system was negative for the whole water. We're doing water freezing. No, not gas, it's solid. My bad. Same idea here, okay? So this one is H2O. All right. H2O liquid going to H2O solid. All right, I just wrote that down so you have your notes like it's completed picture. Now we want to talk at high temp, okay? So if you imagine at high temp, this T is really big. It's negative with a negative delta H, but that makes it a smaller delta S, positive, agreed? So your delta S is not going to be as big as this guy, not as positive. It's still positive, but maybe it's only this much positive because of the temperature. Okay, so now my delta S universe, not universe, my surrounding. I'm all over the place. Surrounding is positive, but it's not positive enough. So overall, your universe is still negative. So it's not spontaneous. Okay, so let me write the explanation over here. So this is high temp. At high temp, the heat exchange of system and surrounding makes not a big impact anymore, right? Makes we'll just say does not make. How's that? That's probably better. Does not make a big impact on delta S surrounding. So it's not a huge positive, it's a small positive. So delta S surrounding is a small positive value. And then your delta S system was a negative. So the overall value is, not big enough to make it negative. So delta S universe is negative. So water does not spontaneously freeze at high temps. Okay, so how do we get the delta S surrounding? You gotta remember delta S surrounding is negative delta H over T or negative Q over T. Oh, I should write system. Okay, so basically this idea here explains to you why some temperature is important to determine if things can happen or not spontaneously. Now, let us combine the system and the surrounding determination here. I'm going to ask you to calculate the surrounding and only just determine the signs for the system and then determine if it's spontaneous or not. We're just going to do like just some examples to see it. I'm not going to ask you to calculate both parts here. We'll just do calculate one part and then determine the sign of the system, okay? So everyone go with this here before I move to the next part. So let's talk about combustion of propane gas, okay? Combustion of propane gas. So propane, C3H8. And then you need oxygen. And you make carbon dioxide, 3 moles. You make 4 water. So that's just combustion for you. Now, they gave you this equation here, and they'll give you, okay, delta H of this reaction is negative 2044 kilojoules. So when they say this is Chem 1 stuff. So delta H of the system, this is my system. negative 2044 kilojoules per 1 mole of C3H8 per 5 moles of oxygen gas per 3 moles of carbon dioxide per 4 moles of water. So this number here is for this exact reaction of how it's written. Okay, so when it says here, number 1, part A, calculate the entropy change in the surroundings at 25 degrees. Okay, at 25 degrees here, delta S surrounding, remember the formula? Is negative Q system over T in Kelvin or negative delta H of the system over T in Kelvin. Okay, so we got to remember these guys here use Kelvin as unit. Okay, so even though they give you in Celsius, change it to Kelvin. Do we have the delta S of the system, delta H of the system? Yes, we are provided that value. So it's just positive 2044 that goes down here, okay? So positive 2044 kilojoules divided by this in Kelvin, so 298. So I get my answer as positive 6.86 kilojoules per Kelvin. Now, for entropy, they usually don't use kilojoules per Kelvin, they use joules per Kelvin. So I'm gonna go ahead and show you that you can also convert this, okay? So convert it over from kilojoules to joules, you just multiply by 1,000. So it's positive 6.86 times 1,000. So I'll just do 10 to the power 3 joules per Kelvin. Okay, so that's a positive value here. Now it says here the next part, determine the sign of delta S system. So we can determine that. We learned how to do that earlier. So how can we see the sign of delta S? We take a look here. We have 1 mole of gas plus 5 moles of gas, so that's 6 over here, turning into 3 moles of gas plus 4 moles of gas, which is 7 over here. From 6 moles of gas going to 7 moles of gas, your delta S system sign should be, what do you guys think? So 6 moles gas, right, it's going to be positive, very good. Going to 7 moles of gas. Delta S system is positive. So combine these two here. The surrounding is positive, the system is positive. You can say for sure the delta S universe here at this temperature, because this is positive at that temperature, and we can tell the system is positive. Delta S universe is going to be a positive value. So it will be a spontaneous process. Okay? All right, so let's do another example here. Everyone go with this? Okay, I'm gonna go to the next part. So the next question is 2O2 plus N2 gas going to 2NO2 gas. Delta H for this system is positive 66.4 kilojoules at 25 Celsius. So they say number 1, find delta S surrounding. Number 2, find sign of delta S system. And then number 3, find the delta S of the universe and see if it's spontaneous or not. Okay, so to do delta S surrounding, we'll go ahead and do that. Delta S surrounding, the formula was negative delta H system over T in Kelvin, which is that number, and then 298 Kelvin here. So negative of that, so negative 66.4 kilojoules. over 298 Kelvin. So I'm going to get negative 0.223 kilojoules per Kelvin. And then we can always convert it to joules by multiplying by 1,000. So you'll get 223 negative 223 joules per Kelvin. Okay, so that's a negative value. Let's take a look at the sign of the system. So it's 2 moles of gas in the product and 3 moles of gas in the reactant. So it's 3 moles gas turning into 2 moles of gas. So my delta S here is negative system. Agree? So because my system is negative, my surrounding is negative, my delta S universe will be negative. So now we can know this is non-spontaneous. EOUS. Okay, so the last time we were in class, we talked about being able to determine a delta S universe, and if it's positive for delta S universe, it'll be spontaneous. If it's a negative for delta S universe, it'll be a non-spontaneous process. So the next part is I wanted to show you the relationship between delta S universe and something called Gibbs free energy, okay? All right, so what we learned before this is delta S universe is equal to delta S system plus delta S surrounding. And then now what I want to do is manipulate this reaction equation a little bit. I am going to multiply this entire reaction with negative delta T, okay? And also I need to remember that this guy's formula, delta S surrounding, remember we had a formula. What was the formula here? It was negative delta H system over T. That's the same thing. That's from the formula we just learned before this. Remember, it could be negative Q also, but we're going to call it delta H because Q and delta H are the same under constant pressure and divided by T. Now, recognizing this, I am going to go ahead and multiply this entire thing with negative T. So I'm going to have negative T times delta S universe equals to negative T times delta S system. And then plus, okay, negative T times, I'm going to, instead of writing delta S surrounding, I'm going to write that term, delta H system over T. So if you notice, this crosses out. This negative T and this negative T here will cross out. Okay, now this equals to then negative T delta S universe equals to negative T delta S system. And then because those cross out, now it's just plus delta H system. Okay, now what is this term here? This term equals to delta G system. So Gibbs free energy's formula is negative T times delta S universe, okay? And that equals to delta G. So I guess I can write it on the side here. Delta G system is negative T delta S universe. So that becomes that here. And then I'm just going to tidy up this equation. Instead of writing the negative T delta S system first, I'm going to write the delta H first. So it's going to look like this. Delta H system minus T delta S system. Okay, this is the formula you're going to want to memorize because this is the Gibbs free energy formula. Okay. So based on this equation here, because we knew earlier that for it to be spontaneous, delta S universe must be positive, and because delta G is the negative sign of that, because it's negative T times delta S universe, when delta G system is negative, it's a spontaneous process. Okay? If delta G is a positive term, then that means the universe was negative for delta S, then it will be non-spontaneous. Okay? So, gotta remember that. And that is because delta G is going to be a negative sign of delta S universe. Now, once we have this here, Gibbs free energy here is going to be able to tell us if it's spontaneous or non-spontaneous depending on what we calculate using this formula. So we can easily calculate the Gibbs free energy, see if it's positive or negative by looking at the delta H of the system, which is usually given or easily determined, and then times the minus T, which is temperature in Kelvin, times delta S system. Okay, so now we manipulated the equation so you can actually look at just the system alone and determine if it's spontaneous or non-spontaneous. All right, so that's the equation we have. I want you to try, we're going to try to apply the situation here. Now, because temperature is here, and we have scenarios where we have low temperature and high temperature, there's actually a table in our slides I wanted to show you. So here's what they were talking about. We'll be talking about Q and K in the last part of this chapter, but basically our equation is delta G is delta H minus T delta S. I just showed you how we got that. And they talked about the information here. Now, if you get delta G is 0, it's at equilibrium. Okay? If it's spontaneous, non-spontaneous, it's not going to be 0 here. But what we're going to look at is it going to focus? There we go. Is this table here. Okay? Now, this table here tells you if I have a combination of delta H system and delta S system, if its signs are positive or negative, under low temperature or high temperature, if the process is going to be spontaneous or not. And then they give you examples here. So I'm going to teach you a way to find a way to use that equation that I just showed you to actually build this table, and you don't have to memorize it. It's very simple trick here, okay? Now, if you find that little math thing I show you about the examples is too complicated for you and you just want to memorize, you can memorize this, that's fine. But I tend to not want to memorize as much as I can because I find that when I'm panicking during a test, I tend to remember things wrongly. So I like to be able to deduce my answers. Remembering certain formulas and then coming up with the answer. So I'm going to show you how we could do this, okay? So here's an example. Let's take a look at a scenario where we have a phase change, okay? So if we have phase change such as ice melting, do you remember what the delta H sign and the delta S signs are for ice melting? And remember I said any phase changes, the delta H and delta S signs are going to be the same. Ice melting is going from what phase to what phase? It's going from solid to liquid. So it's going up in your energy scale. Okay? So do you guys see what sign that is then for your delta H and your delta S? You guys awake? Do we remember is positive or negative here? Okay, it is positive, okay? Now, if you don't remember, Take a look at last class. We talked about it right here under this page here where we talked about endo or exo, what signs they are. And I said phase changes have the same signs for S and H, okay? Now, so going back to this example here, so we're just pulling from what we learned last time. Ice melting is going to be positive signs for both of them. Now, well, logically, you know when ice melts. When does ice melt? Does it melt when it's cold? Does it melt when it's hot? It melts at high temp, right? So we're going to try to use this equation here to determine, to prove that at high temp, this delta G will be a negative number, low temp. But since you already know the answer, it's kind of easy to remember also, okay? So we have positive and positive. We have two temperatures, low temp and high temp, and we have to calculate the delta G. Okay, if the delta G comes out as a negative number, it will be spontaneous. Delta G comes out positive, it will be non-spontaneous. So my formula is delta G equals to delta H minus T delta S. Now these are all in system. I'm going to drop the system term so I don't have to write it as many times, okay? I mean, not as many letters here. Okay, now the trick is, if you have positive and positive, whatever the sign is, you just symbolize this sign with +1 as a number. If it's a negative sign, just put -1. If it's negative here, put -1. So whatever the sign is, put a 1 next to it, okay? And for low temp, represent this with 0.1. And for high temp, we want a big number, so we'll just put 10. So I mean, 10 and 0.1 is a pretty big difference. So that's what I'm going to stick with, okay? So then you start plugging it into this equation here. So low temp, I'm going to use T as 0.1. My H is +1. My S is +1. And when I calculate this, I want to find out if my G is positive or negative, okay? So let's do that. Delta H is +1 minus low temp 0.1 times S is +1. So I'm going to get positive answer here is 0.9. Now, because this is positive here, I know this part is non-spontaneous because it's added as a positive sign here, okay? So because it's positive, it's non-spontaneous. Then we go look at high temp here. Delta G is, again, H is +1, S is +1. And then because it's high temp, we'll put 10 for the T right here. So +1 minus 10 times +1. And my answer here is going to come out as -9. So because it's negative, I can tell it's going to be spontaneous. So just by looking at the sign of your answer for G, okay? So that means whenever you see a process that's positive H and positive S, it will be spontaneous at high temp and non-spontaneous at low temp. So you can see from that table that we just had, you look for the ++, we just did that example, and you can see low temp is non-spontaneous, high temp is spontaneous. So that's one way to put it together. So this little trick here will work for any scenario that you can have. And then this skill is very important because there will be questions where they ask you, take a look at this reaction and you will have to determine the H and S sign on your own. And then they'll say, based on this, can you tell if it's spontaneous at low temp, high temp, or non-spontaneous at those temperatures? You just have to determine it. So that's one example here. But obviously, if you can correlate ice melting to plus and plus, then you remember ice melts when it's hot. So it's also easy to remember that way. Okay, so that's one scenario. Now, since we're doing one phase change, let's do another phase change. We're going to do the opposite where it's coming down. Okay, so one example for coming down is maybe instead of ice melting, we want to go ahead and freeze the water into ice now. Okay, we'll do the opposite direction now. So in this case here, now my solid is still on the bottom, my liquid is still on the top, but now I'm going from liquid down to solid. So this process here is exothermic. So my delta H is going to be a negative sign. My delta S is also going to be negative. Remember, because phase changes will have the same signs. Okay, so that's this part here. Now, let's go ahead and, well, obviously, just by looking at this, you know when water freezes. Water freezes when it's cold, and when it's hot, it's not going to freeze automatically. So you'll know the answer when you calculate your delta G. The low temp will have the negative number. But if you didn't know that, if you don't remember how to do this, we can still compute it. So all I have to do is set up two scenarios, low temp, and I'll set up another scenario for high temp. Okay, and then remember, if I have negative and negative, I'm going to symbolize these with -1 numbers. And then low temp, I'm going to symbolize with 0.1. High temp, I'll just give a big number, symbolize it with 10, okay? And then we plug it into the equation to see what delta G comes up to be, if it's positive or negative. So delta G equals to delta H minus T delta S. So in this case here, it's negative H, negative S, and my T for low temp is 0.1. So let's plug it in, -1 minus 0.1 times -1, okay? Now, then this should give you -0.9, which then low temp is going to be spontaneous. We know that because logically, you know water freezes when it's cold. All right, and then delta G, and then you have delta H minus T delta S. But this time we're gonna put 10 in the temperature because it's high temp. So if you put -1 here, minus 10 times -1, you get your answer as +9. So that means this is going to be non-spontaneous. Okay, so this is just a way I'm teaching you, showing you how you can just use the formula and plug in some numbers here to judge if it's spontaneous or not at high or low temps. Okay, always works. Now let's try another scenario now. Okay, so let's do one with that's not a phase change, because we knew phase change had signs that were the same here. Let's do one where it's not the same. H and S might not be the same sign because it's not a phase change anymore. Okay, so everyone gets so far. I'm going to go ahead and change to the next page. Now, the next one I want to try is, let's have this equation here. We have 2O2 gas plus N2 gas, and then we'll have it turn to 2NO2 gas, okay? And then delta H with this reaction is positive 66.4 kilojoules. Okay, so so this is just basically an example of a reaction. Like, so this question would be, here's this reaction, and here's the delta H. Can you tell me if this reaction is spontaneous or low temp or high temp? That will be the question. So when you see something like this, then you'll have to determine, okay, well, they just gave me the delta H, so I know that's positive. Let's take a look at delta S of the system. So delta S of the system, based on this question, is I have 3 moles of gas turning into 2 moles of gas. So the disorder is going down because you have 3 moles gas turning into 2 moles gas. So I know my delta S sign here is going to be negative. Okay, so now that you know this information here, we're going to set up a scenario where delta H is positive and delta S is negative. Since we're not actually calculating a real number, that's why we're just going to plug in simple numbers here, okay? So when I say positive here, remember we'll symbolize it with +1. When I say it's negative, we'll symbolize it with -1. And then we'll put it under low temp, and we'll put it under high temp. And then we'll be able to see when it's spontaneous. Low temp will be 0.1, high temp will be 10, and then we plug in our equation again, okay? So our equation here delta G equals to delta H minus T delta S, where H is positive 1, S is negative 1, low temp is 0.1. So let's go ahead and plug that in. Plus 1 minus 0.1 times negative 1, and I get positive 1.1. So this is non-spontaneous at low temp. Okay, and then let's take a look at high temp. So at high temp, delta G equals to delta H minus T delta S, where my H is plus 1, S is negative 1, high temp will be 10. So let's plug it in. Plus 1 minus 10 times negative 1. My answer here is going to be positive 11. That's really big, so it's still positive, so that means it's also non-spontaneous at high temp. No, so this is a scenario where you have non-spontaneous at all temperatures. Okay, so that's one example. And that would fit on the table as well. So if you were just to memorize the table, it's all on this little table here, okay? I'm just breaking it down to show you how you can actually put in simple numbers and figure out if it's spontaneous or not just by plugging in ones and tens and 0.1s. Let's try one more example here, okay? Obviously, I'm going to do now the other one, the leftover. So here's my example. We're going to do the combustion of propane here, okay? So it's going to be C3. Sorry, this is a 3. Let me erase that. C3H8. Okay, and then gas plus 5O2 gas turns to 3CO2 gas plus 4H2O gas. And then the delta H for this reaction is negative 2044 kilojoules. So based on this, just by this question statement here, you know your delta H sign is negative, okay? And then my delta H sign is negative. Let's determine the delta S sign. So I have 1 mole of gas plus 5 moles of gas. So 6 moles of gas is going to turn to 3 plus 4, 7 moles of gas. So that means my delta S for the system is going to be a positive sign because this order is going to increase. So with that, now I know my system has delta H negative, delta S positive, and I can compute the low temp and the high temp. Low temp will be 0.1, high temp will be 10. Okay, so we'll do the same thing again. And we just plug in the formula, delta G equals to delta H minus T delta S. And where H here is negative 1, S is positive 1, low temp is 0.1. So negative 1 minus 0.1 times positive 1, and we're going to get negative 1.1. So we can tell this is spontaneous at low temperature. Okay, now let's do the high temperature scenario, delta G equals to delta H minus T delta S, where you have negative 1 for H, minus 10 for high temp, and positive 1 for delta S. If you notice, this also becomes a negative number. So this question here, this reaction is spontaneous at low temp and at high temp. So that means it's spontaneous at all temperatures. Okay, everyone good with this? So this is the table that I was showing you on that slide 33, but we're breaking it down so you can do it with multiple scenarios here. And the questions you're very likely to see on the test is they'll give you a reaction with a delta H, and then they'll ask you if it's spontaneous or low or high temp. Or they'll give you a phase change, like say when sweat evaporates, can you tell if it's spontaneous or low or high temp? Stuff like that, okay? All right. So let's continue and do more problems now. Let's go ahead and now actually calculate the delta G with all numbers. And this is just basically trying to determine the spontaneity at different temperatures. You don't have to do anything on this type of question. This type of question is just asking you, use this knowledge here to determine spontaneity at low or high temp. Now, the next type of question, you will have to use numbers to calculate the actual delta G number. This is just estimating if it's higher spontaneous or not. Okay, so we will be doing an example now. Now we want to go to the next part where we will be using these delta H values and delta S values and temp to actually calculate the delta G values. This is just an estimation here. All right, so let's go and do that question here. So I'm going to just write on the bottom here, okay? So here's my equation. It's going to be CCl4 gas, and it's going to turn to C carbon. It's going to be graphite, so solid graphite form, and then plus 2Cl2, and this will be in gas form. Okay, and it says here the delta H of the system is positive 95.7 kilojoules. The delta S of the system is positive 142.2 joules per Kelvin, and the temperature for this whole system is going to be at 25 degrees Celsius. And then we'll say calculate delta G system and determine if it is spontaneous at 25 degrees, which is at this temperature, if it's going to be spontaneous or not. So with that, then all you do is you take your H and you take your S and you plug it into the formula. And of course, you have your temperature as well. There are a few common mistakes that students will make here. Number one, you have to recognize that this is in kilojoules and this is in joules. And the temperature unit must be Kelvin. So never use Celsius. So students sometimes they just plug the number as is into the equation, automatically getting it wrong. Okay, so number one, you have to remember to convert your units over. So I like to just remember kilojoules is 1,000 joules. So I just take this number and times 1,000, and then I'll have everything in joules, and then I'll always just turn it to Kelvin. Okay, so what I'm going to do is go delta G is equal to delta H minus T delta S. So my H is going to be 95.7 times 1,000 because it's kilojoules, so I have to times 1,000. So 95.7 times 1,000, and there's a positive sign, so I'll pick that. And now this is going to be joules. Okay, because I times 1,000 because that's the kilo right there. Now, and then minus T, my T is in Kelvin, so 25 degrees is going to be 298 Kelvin. And then times delta S, which is this number, positive 142.2 joules per Kelvin. So you notice here the Kelvin and Kelvin then matches and they can cancel off. If you use Celsius here, then it wouldn't cancel the Kelvin and you'll be in trouble. Okay, and also you have to make sure it's joules and joules. So that's basically the trick to it. A lot of people forget to convert units. So make sure you mark on your notes, like you must make sure your units match. So then you get your answer, you put it together in your calculator. You should get a positive 5.33 times 10 to the power 4 joules. Okay, now that's a big number, so we can easily convert it back to kilojoules by dividing by 1,000. So you get positive 53.3 kilojoules. Okay, now because it's positive, reaction is non-spontaneous at 25 degrees. Okay, so all you have to do is just remember to use the equation and always remember to use the correct units. Now, because we know this is non-spontaneous, let's find out what temp will it be spontaneous. Okay, so this is a case where H and S are positive, So it's kind of like the first example that we did earlier here. Let me flip back. Okay, so you see how this question was a positive, and we determined that at low temp it was non-spontaneous, and at higher temp it can be spontaneous. So they're asking, if it's not spontaneous at 25, how much more do you have to raise the temperature to make this reaction spontaneous? So what I like to do is just, for it to be, to cross over a threshold, it has to turn from positive to negative. So I'm going to set it to 0. So that way, once you cross over the temperature higher than that number, the temperature, you'll be able to see it's spontaneous. Okay. So I'm going to set the delta G line to be 0, because that's when it crosses over from positive to negative. And then you do positive 95.7 times 1,000 joules minus, and we don't know this, we'll just leave the temperature because we're trying to solve for that temperature. And this unit will be in Kelvin. And then we put a positive 142.2 joules per Kelvin right here. Okay, so to get your temperature, all you have to do is solve for basically T is going to be positive 95.7 times 1,000 joules divided by 142.2 joules per Kelvin. Can you guys see the algebra when I got from this step to this? Do you want me to write it out step by step? Hopefully you guys follow the algebra.
If
Sorry,
you can, please, just so you know I got it.
I can't quite hear. You want me to go ahead and write it out for you guys?
Yeah, I think she's asking for you to write it out.
Okay, I'll go ahead and do that. Okay, so this is algebra. You want to get really comfortable with algebra because that's actually one of the prerequisites for this class. So right here, you see how it's a positive and a minus number here. So what I would do is I would go ahead and plus both sides with this term. Because it's a minus here, so I'm plus both sides, okay? So I'm gonna work in a different color, like over here, so you'll see. So that means if I plus both sides with T 142.2, I'm going to get T times 142.2 joules per Kelvin on that 0 side, right? Equals to positive 95.7 times 1,000 joules. You guys see that? And then that way T is just going to be taking that number divided by 142.2. Okay, so positive 95.7 times 1,000 joules divided by 142.2 joules per Kelvin. That's how I got that. I just basically had to do another algebra step in my head. This side goes to that, so I wrote it separately here, and that's how you got to this point here. Okay, so hopefully everyone is following now. So we got here, and then you can plug it in your calculator. You should be able to get, obviously it's going to be big temperature. So the number to cross over at 0 is 673. That means your temperature must be higher than 673. So we'll write down temps above 673 K, reaction will be spontaneous. That's really hot. Okay, so I'll give you guys a few minutes to write this, or a few seconds really, like a page, and then you guys we can do another example of this problem here, okay? So we'll do another example. And let's turn the page. We'll do Al, aluminum, plus Fe2O3 is going to turn to Fe plus Al2O3. Okay, so that's the equation here. And they gave you the delta H and the delta S, so I'm gonna write it out. over here, delta H of the system is negative 847.6 kilojoules. Delta S of the system is negative 41.3 joules per Kelvin. And we're going to do this at 25 degrees Celsius. Okay, so now we want to calculate delta G and determine if it's spontaneous or not. So I'll write that down. Find delta G, determine if spontaneous at 25 degrees Celsius. Okay, so we're going to do the exact same thing that we just did. Now, equation here is going to be delta G equals a delta H minus T delta S. Now, these are all for the system here. So I didn't write the system, but these are all referencing to the system. The system is the reaction, okay? So let's go ahead and plug it in. Now, remember, you must change the units to make sure. So I like to change to joule and Kelvin. So I'm just going to take this number, literally write it out, and then just times 1,000 behind it. So I don't have to do like a lot. I can just type it in my calculator. Negative 847.6 times 1,000, that's in joules, and minus T, which is 298 Kelvin, times negative 41.3 joules per Kelvin. Okay, so when we do this, we get a negative answer of a negative 8.353 times 10 to the power 5 joules here. So it says here this is going to be spontaneous because it's a negative number and the temperature we used was at 25 Celsius. I'm going to go here, spontaneous at 25 degrees Celsius. Okay, so we can also calculate what temperature will it be non-spontaneous. Okay, so looking at the scenario here, it was a negative. So it's kind of like the second example that we did here. So the first example earlier was ice melting, and we say ice melts when it's hot, and the opposite here where it's negative, wasn't it negative? Yeah, it's negative. So it's going to be, we can see water freezes when it's cold, but when it's hot, it's non-spontaneous. And we just found out it is spontaneous at 25 degrees. So if you wanted to look for the temperature where it becomes non-spontaneous, it's going to be a high temperature there. Okay, so we want to look for a high temp here. So it says, what temp will it be non-spontaneous? We do the same thing again, OUS. Okay, we'll plug it in. Instead of putting the delta G, we'll set this to 0. We'll leave the temperature empty and solve for the temperature. So 0 equals to negative 847.6 times 1,000 joules minus T times negative 41.3 joules per Kelvin. Okay, again, we do the same thing here. So I'll write down, so this is going to be, so let me rewrite this because now you have negative and negative. So that 0 equals to negative 847.6 times 1,000 joules. And then because it's negative, I'm just going to write plus T and 41.3 joules per Kelvin. You guys still follow this? Now I can also write T times 41.3 joules per Kelvin equals to positive 847.6 times 1,000 joules. Do you guys still follow this algebra here? Because all I'm doing now is take both sides and plus 847, 1,000. That's why I got this here. Okay? And then to solve for T, you get positive 847.6 times 1,000 joules divided by 41.3 joules per Kelvin. And you will be able to find your answer in Kelvin here, which is going to be a really, really high temperature. So anything above this temp, 205 23 Kelvin, it will be non-spontaneous. Okay. All right, so those are the examples we wanted to take a look at for calculating delta G. Now I want to take a look at delta S a little bit here to show you delta S as standard conditions, like on table values, okay? So we're going to look at slide number 41. So you got to remember from Chem 1, we had some tables that had delta H naught. So this naught sign is for standard conditions. Okay, so for standard conditions, here are some examples if you forgot. Gas at standard condition is going to be pure gas at 1 atm. Solid and liquid is going to be at 1 atm pressure. And usually our temperature for our thermodynamics chapter is going to be 25 degrees. I guess you guys probably might remember when we were doing ideal gas law, the standard there was actually 0. But for our thermodynamics, we're going to be using 25 usually. And for solution, for it to be standard, it should be in 1 molarity concentration. So these are standard conditions, okay? When you have something that's standard, the values can have a not sign on it. So instead of just a standard regular delta S, if you see a standard, that means it's under standard conditions, okay? So this not sign here tells you it's standard. Now, we can actually, if you remember, here, let me pull up the table. You'll be able to see this chart. So I'm pulling out this gigantic textbook here. It's so heavy. Hold on. Oh, here it is. Whoa. See this? Remember this delta HF not, delta GF standard not here, right? These are the stuff you learned. This table here you learned in Chem 1. Where you learn that some guys have zeros. The guys that are 0 is because they're the most stable form of that pure element at standard conditions. So don't worry if you forgot about it. I'll try to write it down in our notes later. So those guys have zeros, and then we'll learn later on also. So we're going to do this one first, and then we'll do this. But just know that delta G and delta F is literally going to be the same pattern. If the H formation is 0, the G formation is also 0. But the S will never, never, never be 0. So I'll explain why. So you see here, S is no zeros here, and you have some zeros. So tungsten, the most stable form of tungsten is solid. So you have 0 for the H and 0 for the G of formation. But for the entropy, you never have a 0, okay? Because only perfect crystals at absolute 0 will have a 0 value for S, and nobody does, okay? And then if you flip, and then there's all these pages here, like it's pages and pages, but obviously that's why we don't have to memorize this. But if you notice, every single element will have a 0, because those zeros that it says here, this means nickel solid is the most stable form for nickel, and the H is 0 formation, G formation is also 0. But if you notice, the S is never 0 here. If you wanted to look at phosphorus, the white solid phosphorus is the standard 0, which is the most stable form. And even the solid red, that one's not the most stable form, so it has a number here. Okay, so that's what we're going to look at. I'm going to explain to you how we can qualitatively decide who has a bigger S and who has a smaller S, but we don't know the numbers until you refer to the table. Okay, moral of the story is G and H and G will have zeros, S will never have zeros. Okay, and these are all formation values from the table. So if you keep going, like there's tons of it. So when you're doing your homework, you'll have to click on the link to pull the tables up so you can look these values up. On the test, and I like to provide these values for you, okay? All right, so I can move this gigantic book away. So we are going to talk about the delta S formation and how only the perfect crystal at absolute 0, which is 0 Kelvin, has 0 for delta for your S standard. That means everybody won't have a 0. That's why the table has no 0 for S at all. Okay, only the perfect crystal at 0 Kelvin has it. We're obviously not doing anything at 0 Kelvin. So the standard absolute entropy, remember, the sign here, the not sign means it's standard. Okay, now as usual, S here is an extensive property. So what we have been learning for all the thermodynamics, they're all extensive properties. H was extensive, enthalpy, that was H. And then E was extensive, that was internal energy. And then we learned G, Gibbs free energy, and then we have S. All of these guys are extensive properties. So what does an extensive property mean? Hopefully you guys remember this. So there's intensive property and extensive property from Chem 1, where intensive property does not change with the amount of matter you have. Like say density is an intensive property because a small amount of water versus a big amount of water will have the same density, right? But a small amount of water and a big amount of water will have different masses because mass is an extensive property. It depends on how much of the stuff you have. Another example is volume. If you have a small amount of water versus a big amount of water, the volume is going to be different. So volume is another extensive property. If you wanted to talk about another example of intensive property, maybe we'll talk about freezing point. Freezing point of water, whether it's small amount or big amount, it should freeze at the same temperature if all other conditions stay the same. Okay, so basically the definition here, it says entropy is for 1 mole of a substance at the standard, which is 25 degrees to 98 Kelvin for whatever the state is. Okay, so here's a few examples of the values that I put in. That was a much bigger table I showed you earlier. This is just an abbreviated version of the table. But if one thing you can take home is nobody here has a 0. Now, if you were to look, H2 gas, hydrogen gas, is the most common form of hydrogen. And this, because it's so common, it's because it's so stable. So that means the most stable form of that element will be 0 for H formation and G formation standard. So this guy here, if you were to look at the table, H2 gas would have a 0 for H and G, but then it would have this value for the S. And then also another common gas in our atmosphere is nitrogen, right? Nitrogen, like gas, is so prominent that because it's most stable form of nitrogen. So if you were to look at the S from the table, it's 191.6, but you would see the nitrogen here is going to have 0 for H and 0 for G, okay? And then you also see oxygen. Oxygen is really common because we breathe it in. So you see oxygen gas, O2 gas form. If you look on the table, you'll see the 0, 0 for the H stuff too, H and G. Let me actually pull the table back up and show you guys. So on this page, you see here the oxygen value here? See, O by itself is not the most stable form, but O2 is the most stable form. That's why you saw the 0, 0. And O3 isn't, so it'll have a number. So you'll see like for nitrogen here, what's the most common form of nitrogen that you see is going to be an N2 gas, and that's why those are 0, 0. It's most common because it's most stable. And the guys that are most stable are going to be 0. So mercury is always going to be in liquid form, so that's a 0. Most metals will be in a solid form. So manganese here, and then nickel, and then platinum, if you can see on this side. And then you have potassium, so right here. I don't expect you to memorize this, but I do expect you to know like which common gases, like nitrogen gas, oxygen gas, like those in your atmosphere, okay? Because those guys are 0, you should know they're 0. Sometimes I will not provide the delta H for the 0 guys because I expect you to know those are 0. I wouldn't do that on it would be one of these common gases here, okay? But a lot of times they don't provide it to you because you should know that's a 0. Just try to check if it's the most stable form of the element. All right, let's go back here. Put that book away. So if we were to just relatively judge who's higher and who's lower, okay? A liquid is going to be less disordered than gas, so the gas will have a higher standard S, standard entropy, okay? Just because of the phase. So if you have like solid will be even smaller than this. And then if you were to look at molar masses, the bigger the molar mass, the heavier it is, the more disorder it will be, so the bigger the S from S standard will be. Okay, so number one is what phase is it? And then number two is the heavier it is, the more S standard entropy it will be. And then depending on what kind of bonding stability, diamond is bonded covalently from one carbon atom to another, all of them covalent bonds, versus graphite sheets are actually covalent bonding within 2D dimension in just one sheet, but from one sheet to another sheet is actually a London dispersion or van der Waals interaction. You guys remember van der Waals and London dispersion? So this was that, okay? So because this guy is not covalently bonded, it has more degrees of freedom. So graphite will have a bigger S standard than diamond will be. Okay, now over here, the next thing is if you run into something, even if like the molar mass, as long as you have 2 atoms versus 1 atom, the 2 atoms has a lot more different configuration that can take place. So by default, the more number of atoms you have, the more disorder it will be, so my S standard will be bigger. So even though argon is heavier, but because NO has 2 atoms in it, the S is actually going to be bigger for that guy. Okay, so and then if you were to dissolve anything, remember we talked about sugar, 1 piece of sugar dissolved in a lot of little pieces. So if you had a salt here, KClO3, which is solid, and then you dissolved it, it broke into ion pieces. The ions are a lot more pieces than just 1 piece of salt. So then your disorder, your entropy also should go up. Okay, so now based on this here, you will have like, usually you will be given a list of like S here. I'm just showing you how to determine like qualitatively, but if they gave you a table of all the values, you should be able to calculate the S of your system. So I'm going to give you an example for that now, okay? So the example we have here is, first one we're going to do is we're going to do 4NH3 gas plus 5O2 gas is going to turn into 4NO gas plus 6H2O gas, okay? And the values will be given on the table and it will be provided in this question here. So S standard here, the unit is in joules per moles Kelvin, because it's per mole of that item. So I'm going to write out 1 mole of the item of this guy is going to have 192.8 joules per moles Kelvin. And then the next one is O2 gas. And because now O2 is the most common form of oxygen. So if I were to ask you for H or G, those are zeros. But because it's S, S will never have a 0. S actually has a value for this guy, 205.2. Okay? And then NO is the next thing in line here. NO's number is 210.8. And then you have H2O gas, which is 188.8. Now remember, the chemicals that only has the zeros for H and delta H formation and delta G formation that are zeros, it's only going to be pure element at its most stable form. So these guys aren't even pure elements, they're compounds. Okay? So they will never have 0, but O2 is an element and it's the most stable form of that pure element. In standard condition, the H and G will be 0. However, we are talking about S in this question and they don't have a 0 for S. So to calculate this, because it's a state function again, like H, like G, you will take the final state minus the initial state. Now the final state would be my product state, and then was minus the initial, which is the reactant state. So basically you have to take the total of the products minus total of the reactants, okay? So we take the final, so total of the products minus total of the reactants. So I'm going to go ahead and write it out here. So I'm going to start with my products. So I have 4 of NO, so I'm going to write 4 times each mole of NO is 210.8, right? So you have to remember times mole because this is per 1 mole and you have 4 moles in your equation. So 4 times 210.8, that's one of my product. And then I have to add this product too. I have 6 of that guy, H2O gas, and 6 of 188.8. So this is a total of my products here. So I'm going to go ahead and put a big thing around it and say these are all my products. And then I want to minus all of my reactants. So let's count what reactants I have here. I have 4 times 192.8. And then I also have 5 times 205.2. And then you close it off. Okay, so when you do your calculations, you remember it's products minus reactants. Doesn't this look just like what you did in Chem 1? In Chem 1, all you did was, instead of S, it was H. So the way to do is exactly the same. Take product, total of products minus total of reactants. You have to be careful when you do this in your calculator. If you do this together, this will be minusing this whole term here. If you're doing one step at a time, remember this is negative here, but this, sometimes people forget and then they still use a positive here. This actually turns it into a negative because of the minus sign. So depending on how you do your calculation, okay? Just be aware of that. Sometimes people forget. Another common mistake is students forget to multiply with the coefficients. That's another common error, okay? So make sure you are aware of that. And if you just put in products minus reactants, you should be able to get the answer. So this one here is going to come up to 178.8 joules per Kelvin, because we obviously multiplied the moles out already, so we have joules per Kelvin left. Okay, everyone good so far? So I want to try another question, same type. We also still do products minus reactants, okay? I'm going to go ahead and move it to the next page. So the next question we want to do now, we're going to write out the equation. It's going to be 2H2 gas plus O2 gas going to 2H2O gas. Okay, and I'm going to give you the S values on the side on a little table here. So S standard is going to be joules per moles Kelvin, because it's going to be 1 mole of my item. So 1 mole of H2 gas, the S will be 130.6. And then 1 mole of O2 gas, the S will be 205.2. 1 mole of H2O gas, the S will be 188.8. So remember, if we were looking H2, the common form of hydrogen, most stable form, and O2, the most stable form of oxygen. If we were doing G or H calculations here, these guys would have been 0 values, okay? So just keep that in mind. So to do the delta S for the reaction, so this is for the reaction. So sometimes I will actually write out reaction. It's the same thing, RxN, okay? But it's saying all the products minus all the reactants, okay? So I have 2 of H2O gas. So I'm gonna write 2 of H2O gas, which is 2 times 188.8. And close this off because this is my only product, minus all my reactants. So I have 2 of H2, 2 times 130.6, and then plus 1 mole of 205.2. Close that off. I should be able to get my answer. And this one comes up to be negative 88.7 joules per Kelvin. Okay, so that's to do S, right? So like I hinted around earlier, we did this for H in Chem 1. We can do it for S, and obviously we can do it for G also. Okay, so if they give you a G, maybe they'll give you a table with all the G values and you take the final minus initial. So that's another way to do it, okay? But here's another question that is going to make you take the final initial for the H and the S so you can calculate the G. Okay, this is the most tedious form of calculation, but if you see this question, you'll know how to do it. So I'll write the question out and we'll work it out together, okay? So here's the equation. It's SO2 gas plus half of O2 gas. and it turns into SO3 gas. Okay, it says, the question says, find delta G standard for this reaction at 25 degrees Celsius. Determine if it is spontaneous. Okay, now instead of giving you the delta G straight from the table, you know what they're doing here? They're going to give you the delta H for the table, and they're going to give you the S of from the table. Okay, so the unit for delta H is kilojoules per mole. So if they gave you the G, it would have been much easier. Just take the products minus reactants. But because they didn't, they gave you the H and S. You can still do it. Okay. They'll give you the table values of these guys. So you'll have values for SO2 gas, O2 gas, and SO3 gas. Okay, now, remember what's the value for this guy? 0. Okay, the G would also have been 0, but we don't have a table set for G here, so we're going to do just the H here, 0. Okay, a lot of times because it's 0, I actually don't even list it in my test. I just leave it blank, assuming you know it's 0. So make sure you know that's a 0 there, okay? But these guys, because they're not elements, are going to have numbers, and you cannot solve the problem without it. So you will be provided these values. This one is negative 296.8. The bottom one, SO3, is negative 395.7. Now let's go to the S values. Nobody has a 0 there, so you need all the values given. So 248.2 is the value for S for SO2. For O2, the value is 205.2. For SO3, the value is 256.8. Okay, so what we actually have to do to find the delta G is you have to compute the delta H of the system and the delta S of the system using these values. And then plug it into this equation where delta G of the system or the reaction equals to delta H. Okay, since I wrote system. Actually, I should write reaction. System and reaction is the same thing, okay? Sometimes I write system, sometimes I write reaction. I really mean the same thing. So I'm going to keep it reaction because the question says reaction here. So don't mind me while I erase this and write over that. Actually, while I'm at it, let's write this out. So it's RXN for reaction. Okay, so now all we do is do this, products minus reactants, and then get that answer, put it in here, and put 298 in there. Okay, so let's get going. Let's do the first one. We'll do the H first. Delta H of my reaction equals to the total of products minus reactants. So my product is SO3. I have 1 mole of it. 1 mole times negative 395.7 because we're doing H first, okay? And then that's all my products. I'm gonna close it off. Minus all my reactants, which is 1 mole of SO2. So it's 1 times negative 296.8 plus half mole of 0. So I really didn't have to write it, but I'm gonna write it anyway. There we go. Okay. So this part here is going to give us an answer because remember this is in kilojoules here and this is times the number of moles. Our answer is going to be in kilojoules. Okay, so here's another trick. Remember earlier they were giving H in kilojoules and then S was in joules. You'll have the same problem here. You have to remember to convert your units later. So in this case here, I actually got negative 98.9 kilojoules and I can actually go ahead and just times that by 1,000 so I know it's in joules. So it's negative 98.9 times 1,000 joules. Okay, so that's that one part. Let's go ahead and do the same for delta S. Products minus reactants, okay? So let's do the product. 1 mole of SO3, which is 256.8. And then minus 1 mole of SO2. So this is 248.2 plus half mole of 205.2. And remember, this unit here is going to be in joules per Kelvin. Okay, because it's joules per moles Kelvin, and we already multiplied with the mole, so it's going to be in joules per Kelvin. So see how this has to be joules, and that's joules? Same thing like we talked about earlier. So this answer comes out to be negative 94.0. Okay? Now that we have H and S values from the tables, we are going to combine it together into my delta G reaction equation. So delta G of my reaction, which is standard condition, equals to H, which is negative 98.9 times 1,000 joules. That's right here. And then minus T, which I have to do in Kelvin. It says it was 25 degrees, so it's 298. And then S was negative 94.0 joules per Kelvin. So I'm good here. See all my units cancel out. Joules, and Kelvin, and joules will stay. So my answer here is going to be in terms of joules for now, and then I can always convert it to kilojoules later. So my answer here is going to be negative 70.9 times 10 to the power 3 joules. So it's negative 70.9 kilojoules. So because it's negative for delta G, I know this reaction is spontaneous. A lot of times they'll say spontaneous as written, or they'll say spontaneous in the reverse direction. That means it's non-spontaneous, okay? So it just depends on the wording. So this is spontaneous at 25 degrees. So here's another question building off of this problem, okay? The question says, will this reaction be more spontaneous or less spontaneous at 125 degrees Celsius? So they're saying, well, let's do it at a different temperature and see if it's still going to be spontaneous. Is it going to be more spontaneous or less spontaneous, okay? So all you have to do is instead of 298 here, which is 25 degrees, we will put in 398 because it's 125 degrees Celsius. That's the only difference here. So let's go ahead and put that in. So my delta G reaction here now is going to be negative 98.9 times 1,000 joules, and then minus 398 Kelvin because of the new temperature here, and then minus 94.0 joules per Kelvin. And we will get our answer as negative 61.5 times 1,000 joules, or we can say it's negative 61.5 kilojoules. Now, it's still negative, it's still spontaneous, but it's less negative, right? Because this one's like a bigger number, it's more negative. This one's less negative, so it's gonna be less negative, so it's less spontaneous. It's still spontaneous, but it's a little bit less spontaneous. At the 100 degrees higher, okay? So hopefully everyone is doing good here. So I am going to go ahead and write down that statement about the who has 0 and who doesn't have 0, right? Remember we were saying S never has 0, G and H have zeros. I'm gonna write it down on the next page here so we can remember, okay? So everyone good here? I'm gonna go ahead and turn the page. Now if you need a little bit more time, if I turn it before you are ready, let me know, I will flip back for you, okay? But I'm going to go ahead and write that statement on the next page. So remember, delta G formation and delta H formation, they have the same exact things, okay? We learned them, H we learned in Chem 1, but G is literally the same thing. So they will have 0 values. Okay, I guess I should write 0 equals 0 here too. Equals to 0 equals to 0 for elements, pure elements, okay? Elements in most stable form at standard conditions. So for elements, pure elements. And S will never have 0, so delta S has no 0 values because only the perfect crystal at 0 Kelvin. That's 0 Kelvin, not okay, right? 0 Kelvin has F0. So S doesn't have 0 on your tables, but G and H has 0 on the tables. And who are they 0 for? For the pure elements in the most stable form under standard conditions. Okay? Now, with that here, since we just did the H and the S, we'll go ahead and do a question with the G also. Okay? So I'll write out the question. So it's CH4, it's methane. We're going to do combustion of methane here. 8O2 gas. And then it goes to CO2 gas plus 2H2O gas. Oh, this one has 4O3. This is unique. Okay, and then I'll go ahead and write down the delta G formation values here. And the unit for delta G is going to be the same as H is kilojoules per moles, because we're talking 1 mole of each thing. Okay, so 1 mole of CH4 will have negative 50.5. O2, remember O2 is the most stable form, right? So what's this guy's value? 0. Now, a lot of times I don't even give you this value. I just leave it there. You need to know that 0, okay? Now, CO2 is not an element. That's not an element. That's still an element, but it's not the most stable form because that was the stable form. So this one will have a number 2, okay? So CO2's number is negative 394.4. H2O is negative 228.6. O3 is positive 163.2. So when you have a question like this, again, as usual, take the total of the products minus the total of the reactants. Okay? So I'm going to go ahead and write it out for you. I have these guys are my products, and that's my reactant. So my reactant part will be pretty simple because you don't even have to do the oxygen because it's 0. You don't have to write it. Let's do this. So product has 1 times negative 394.4 less 2 times negative 228.6, and then plus 4 times positive 163.2. Close that off because that's all my products. And then minus 1 times negative 50.5, and then 8 times 0. Okay, so you put this together, you end up getting negative 148.3 kilojoules, which means this reaction is spontaneous as written. Sometimes if you get a positive number, they'll just say this reaction is spontaneous in the reverse direction. They really mean to say non-spontaneous as written, but sometimes they word it funny and say spontaneous in the reverse direction. Hess's law. So number 1 says when an equation is reversed, delta G or delta H sign is reversed. Okay, so I can sort of explain this in this picture here. So say you have reactant going to product, that's going up, right? So from R going to P, it's a positive sign, agree? What if you did a reverse reaction where you did P going to R? So P going to R would be a negative sign. But the number, the size of the arrow, the distance is exactly the same because they're at the same positions. We just changed the direction. So basically when we say, if you reverse the reaction, what happens is the size is the same. All you do is change the signs. Okay? So that's where that statement comes from. Now, number two, if you multiply an equation, if an equation is multiplied by, let's say, factor n, delta G or delta H of that reaction, is multiplied by n also. Okay, so you do the same multiplication. So let's say like, oh no, if I wrote this equation like A plus B goes to C and my delta G is 100, right? If I had 2A plus 2B goes to 2C, my delta G is going to be 2 times 100. Because it's the double amount of moles, because this is an extensive property. This 100 here is per A, per 1B, and per 1C. So if you had 2A, then obviously this number had to double up. Okay, and this is because it's an extensive property. So we'll write down these guys here. Extensive property. Okay, remember extensive property? Extensive is the one that changes with the amount. Intensive doesn't change with the amount, okay? All right, then we got a third one. If we add multiple equations together, delta G or delta H of each step is added up as well. Okay, so this is stuff we've learned in Chem 1 before. So remembering these rules shouldn't be too bad. Now, the biggest problem with Hess's law is, you guys remember the manipulating K part in the beginning of the semester, where they like had this equilibrium constant and they did the manipulation, they did some different math operations? Well, that's when people start getting it confused. They mix those two up. You know, when you were doing K, it was a different, when you reverse the equation, you did something else besides reversing the sign. When you multiply the factor n, your K actually is not multiplied by n. So it's different math operation. So I just want you guys to remember that. You need to be able to keep it separate, okay? But the way to do it is the same, it's just the math operation will be different. So if you don't know what I'm talking about, I can flip back to the notes to show you way back in the beginning. So it says, you see how manipulating K, if you reverse it, you do something else with the K, 1 over. When you multiply with the reaction, you take K to the power of that thing. And when you add, then you actually multiply your K. So this part here, people get confused with what we're learning over here. So you want to make sure Hess's law is delta G and delta H. The math operations are actually a lot simpler than what we learn in K. The only time these two will collide is during the final exam. So just make sure you are aware which one is which, okay? All right, let's try some problems on doing Hess's law. We'll start with some exercise here. We'll do some practice as review. So the only thing different here in Chem 2 is that, Chem 1 we used to use delta H only. Now I'm just going to switch it. Instead of delta H, we're going to do delta G. So the question is 3C plus 4H2 to make C3H8. Delta G is something we don't know. Okay, here's what we know. Line 1, C3H8 plus 5O2 equals to 3CO2 plus 4H2O. Delta G naught here is negative 2074 kilojoules. Line 2, we also know this. C plus O2 goes to CO2. Delta G naught for this reaction is negative 394.4. Two H2 plus O2 goes to 2H2O. Delta G naught equals to negative 457.1 kilojoules. Okay, so we have 3 lines here. We gotta decide what we want to do with each line so we can get our answer. So like we did earlier in the semester, all you do is you look for the chemical that doesn't repeat again. Like we pick line 1 first, we start line 1, pick something that appears in line 1 that has to go in the top here, but doesn't repeat itself in line 2 and 3. Okay, that's the easiest way to do it. It's like picking, when you're trying to solve a jigsaw puzzle, you do the corners first. And we're trying to do the corner pieces because they're less confusing. Okay, anything that repeats itself is super confusing. I try to avoid that to start off with. So I see in line 1, you can use C3H8. You cannot use O2 because it repeats. You cannot use CO2 because it repeats. You cannot use water because it repeats. But this guy's okay. You can use that. Now, this guy has to fit up in this picture here. Where does it belong? Is it on the correct side? It's actually on the wrong side. Okay? So see how it's on the opposite side? But it's the correct number of moles. It's 1 mole this guy and 1 mole that. So that's perfect. All I have to do is flip reaction 1. So let me go ahead and write it out. Flip 1. And when I flip 1, what happens? I'm going to just go ahead and write the thing out. 3 CO2 plus 4 H2O goes to C3H8 plus 5O2. Now what happens to my delta G here? It's going to change signs because all I did was I reversed the reaction, the opposite direction. So instead of negative, now it's going to be positive, same exact number, 2074 kilojoules. Okay, now what about line 2? Can you see what we're going to use in line 2 to get it to work? And once you identify it, what operation do you do to line 2? Any ideas, guys?
Multiply by 3.
Right, multiply by 3. That's a good one because we are trying to identify carbon, okay? So these 2 guys we just pointed out repeated itself earlier. So my only option is carbon here, and I can see that it's on the right side, but it's the wrong amount. So to make it match, like we have to multiply by 3. Now once you multiply by 3, I go ahead and write it out. So it's 3C plus 3O2 going to 3CO2. Delta G now is 3 times negative 394.4 because we're talking triple the amount of the original. Okay, let's take a look at line 3. Can you guys tell me what we should do with line 3? Who are we trying to match and what operation should we do?
Trying to match the H2, we want to multiply by 2.
Perfect. We're going to multiply H2 and we need to get 2 because it's on the right side but wrong number. So we'll multiply by 2. I'm going to write it out. 4H2 plus 2O2. And we're going to get 4H2O. So So my delta G here, all I do is the same thing. I multiply by 2 as well. Negative 457.1 kilojoules, and that number was multiplied by 2. So once you do all of that, we essentially match some pieces already. So we got our C3H8 matching. We got that one. And then we got our 3C to match. And we got our 4H2 to match. So we technically got everything in place already, but there's a lot of other distractions happening. The beauty of this part is once you match these chemicals that doesn't repeat, everybody else will cancel off. We can double check this. So what you do is you add all these 3 steps together. So these are all my reactants, and these are all my products. I like to circle them so I know which side they're on. So I have 5O2 here. You saw that? There's 5 over here because there's 3 and there's 2. So that crosses off. I have 3 CO2 here, and I have 3 CO2 here. That crosses off. I have 4 water here. I have 4 water on the other side. That crosses off. So basically, when you add up all these steps, you get 3C plus 4H2 goes to C3H8. Therefore, our delta G now is just addition of all these numbers up together. So if you add them up, being careful with putting parentheses in your calculators and all, it's going to be negative 23 kilojoules. Okay? We don't keep a decimal place here. All right. So hopefully everyone gets that one. We'll do a couple more so you have examples to study from, and you'll see plenty of examples in your homework and quiz too. So CS2 plus 6H2O2 goes to CO2 plus 6H2O plus 2SO2. My delta G is something. You don't know what that is? So we're going to use lines 1, 2, and 3 to solve this. So let me write out what's in line 1. Line 1 is CS2 plus 3O2 goes to CO2 plus 2SO2, where the delta G here is given as negative 1077 kilojoules. That's the first line. Let's go to the second line. H2 plus O2 equals to H2O2. Delta G equals to negative 188 kilojoules. The third line is H2 plus half O2 goes to H2O. Delta G for the third line is negative 286 kilojoule. Okay, so let's take a look at these 3 lines here and try to decide what we want to do, okay? So once you're done writing this question, take some time. Let's approach line 1 and decide what we want to do to line 1. What chemical are we trying to match? And what operation do we do to it?
Would it just stay the same if CS2 matches?
Yes, it would stay the same. Very good. So let's do stay the same. Keep one the same because our CS2 is matching. The other guys are repeating anyway. This one repeats. CO2 doesn't repeat. SO2 doesn't repeat. But if you match one, the others will match if you notice. Okay, we're just matching one here. So we'll keep it the same. CS2 plus 3O2 goes to CO2 plus 2SO2. Delta G stays exactly the same also. Negative 1077 kilojoules. Now, let's go to line 2. Can we do something to line 2? What in the world are we trying to match this time? So over here, H2O2, hopefully you guys can see that, is what we can try to match, right? So H2O2 is on the wrong side, so we do have to flip it. And then we also are trying to match 6 of them. So I would flip and times 6. So very good. So flip times 6. So let's go ahead and write it out. So 6H2O2. So we match that piece. And then plus, no, goes to, gotta write my products now. Six H2 plus 6O2. So my delta G, we have to do two things. We have to change the sign and we have to times 6. So times 6, and then instead of negative, it will be positive 188 kilojoules. So let's go to line 3 now. Line 3, what should we do to line 3? What are we trying to match here?
Is it the H2O and you multiply by 6 as well?
Yes, very good. So we're going to match the H2O here. So we will times 6 because it's on the correct side, and we want to have 6 up here. We only have 1 mole. So let's go ahead and do that. So 6H2 plus, so 6 times half is 3. O2 goes to 6H2O. Now all you do after this, okay, we got a delta G. So delta G is 6 times negative 286. And then we add them up, okay? When you add them up, it always matches if you did not make a mistake somewhere. So let's go ahead and add them up. This is all my reactants. This is all my products. And let's see who cancels off, okay? So first off, we know we match CS2. We also match 6H2O2 to this one up here. And then we match our CO2 up here. We match our 6 waters over here. So we have everything. Oh yeah, we got this one too, 2SO2. Match that one too. So now we have to cancel the other guys off. So 6H2 and 6H2 crosses off. 3 and 3 equals 6. That crosses off over there. So that's perfect. It matches exactly what we're looking for. CS2 plus 6H2O2 goes to CO2 plus 6H2O plus 2SO2. So my delta G will be adding all these guys up together. So adding all these guys together, you should get a negative value, negative 1665 kilojoules. Oh yeah, speaking of negative, since these are negative, these are spontaneous as written. Go ahead and write it out. Spontaneous. Because their delta G is negative. Okay? Are you feeling pretty confident? Here, I want to show you one more example, and then I think we should be, because I'm trying to show you some that are not completely, some of them are really easy, you don't do much. This one's okay, you do flipping, you multiply, you do some flipping and multiplying. So let's do another example, okay? NO plus O goes to NO2. Delta G is, we're looking for it. Line 1, 2O3 goes to 3O2. Delta G equals to positive 489.6 kilojoules. Line 2, O2 goes to 2O. Delta G equals to positive 463.4 kilojoules. Line 3, NO plus O3 goes to NO2 plus O2. Delta G equals to negative 199.5 kilojoules. So these are our 3 lines here, and we want to work it so it gives us the answer. So let's take a look. Now, can you use anything on line 1? And if you do, which one are we trying to match? And line 1 has absolutely nothing that belongs on the main equation. So I can't really use line 1 to match anything, but I can come back to line 1 later on once I have the other guys done and use it to fill in the blanks. Okay, So this is an example where you actually have to skip one of the lines because there's absolutely nothing you can do with the first line for now. Now, then you go to the second line. What are we trying to match in the second line, and what operation do you do for line 2? So we skip line 1, we're going straight to line 2 first.
Would we flip it and divide by 2 to match the O?
Right, we're trying to match it to O. So you do divide it by 2, but because I said in my thing here, I said if you multiply a factor of n, I didn't say divide. Technically, I could have said divide, but since I said multiply, I'm just going to say multiply by half. It's the same thing as divide by 2, okay? And we also had to flip it because we're trying to match this 2O to make it go to O here. So I'm going to go ahead and do that. So 2O becomes O, O2 becomes half O2. And then my delta G here is going to be flip the sign and times half. So negative 463.4 times half, or you can just say divide by 2. That would be for line 2. Now, and then we can go to line 3 and decide what in the world we want to do with line 3. I actually see 2 things that I can match here. You see that? NO and NO2, and it actually falls exactly the same. So that means you do not change line 3, keep it the same. Everyone agree? Now let me know if you guys have questions, okay? By now this should be pretty, nice review. So that's a good thing about this chapter because you have seen all the types of calculation before, not too much new material. So that makes it a little easier to process. Let's go ahead and write it out. Keep line 3 the same. So NO plus O3 goes to NO2 plus O2. My delta G here is going to be the same again, negative 199.5 kilojoules. Now, we have to go back to line 1 now to try to decide what we want to do with line 1. So what are we going to try to do in line 1 to try to figure it out? So let's circle what we already matched. We matched NO, we matched O, and we matched NO2. Okay, so my goal now is to get rid of the O3 and to get rid of the 1.5 O2, right? So what do I do with line 1 then to use it to get rid of O3? We can focus on just one item, just do this one, because the other one will fall into place. So I have 1 O3 so far on the reactant side. I need my line 1 to have 1 O3 on the product side so I can cross it off, right? So how do you do that for line 1? Number 1, you'd have to flip it because it's on the wrong side. Number 2, you have to get rid of the 2 here because you only need 1 mole of O3 on this side. So I would actually have to flip and then multiply it by half. Are y'all following this? So this one's a little bit different, but same idea. It's just using line 1 later on to fill in the blanks. So if I flip it, my O3 comes to the product side and I halved it, now I have 1 O3. Now my O2 goes to the other side, now I have 3 halves of O2, which matches perfectly because I have 3 halves O2 on the opposite side here. So then it will cancel off. Now, once I do this, I have to write down what my delta G is. Delta G is going to be half times line 1 was positive sign, so now let's change it to negative 489.6 kilojoules. Okay, so now I just make sure everything canceled off, right? We cancel O3, we cancel the O2. So we got NO plus O goes to NO2. We gotta add up all these guys here for my delta G. Now when you add them up, this one you should get like negative 676. Okay? All right. So Hess's law should be a nice review. So that's awesome. Now we want to go to the absolute last calculation part for our chapter here. Everyone good with this? I'm going to go ahead and show you the slides now, okay? So we want to do slide number 62 here. Now, the difference between this delta G without the naught means the naught sign has standard states. Remember standard conditions? So a normal state, that temperature, gas will be 1 atm. If it's a solution, it will be 1 molarity. So that standard sign means it's, naught sign means it's standard state. Now, under non-standard condition, delta G and delta G naught are two different things. What you usually see from the table is delta G naught, okay? And they want you to calculate the delta G here. So actually, these values here should have been naught because they're from the table. Let me go ahead and add the naught here so you, table is usually reporting, they usually report, unless they give you this for some parameter that's not standard, they would write it out. If they don't have the delta, I mean, whatever from the table usually is a standard. If it's not, you would be manipulating from the table. So make sure we write that. Like over here, if you wanted to, you can add your naught signs as well. It'll be fine, like whether naught or not. Typically, it's going to be a standard condition. Sometimes it isn't, but either way, the way to do it is the same. But anyway, let's get back to this. So there's the difference. This one is standard, this one is non-standard. To relate non-standard to standard, standard is something you get from the table. A lot of times this one is product minus reactant, that's why you get that. And then they're reported as standard conditions. Now to relate this delta G and delta G naught, the difference is R, T, L, and Q. So Q, remember, is Q and K, our equilibrium stuff. So that's Q. R is a gas constant, T is temperature. So we'll talk about the gas constant here. The R here, you want to use the one with the joules on your periodic table, okay? So this one, you should use 8.314 joules per moles Kelvin, okay? And the T, because this is Kelvin here, your temperature should always be in Kelvin. And then your Q is the usual when we write a reaction quotient. Now, when delta G equals to 0, that means that it's at equilibrium. Remember, if it's negative, it's non-spontaneous. I mean, negative is spontaneous, positive is non-spontaneous. And then if it's 0, it's at equilibrium. So then at equilibrium, this is 0. Then this is at equilibrium. Q turns to K. So you have K over here, RTL, and Q turns to K. And then because that's 0, the delta G can go the opposite side. So that's why one of it has a negative sign here. So delta G naught equals to minus RTL and K. All right. So let's go ahead and do some calculations for the Q and K here. I'll write the question and we will be able to do that. And then we're done with this chapter here. All right. So at 298 Kelvin, here's our first question. So they gave you the temperature in Kelvin, which was nice. If they gave it to you in Celsius, remember you will be using your calculation units as Kelvin anyway. You have to convert. So 2NO plus O2 turns to 2NO2. Delta G naught of this reaction is given as negative 71.2 kilojoules. Find delta G reaction under the following conditions. So the following conditions are not going to be standard because they already gave you the standard one. So what's not standard? Oh, the P of NO, pressure of NO is 0.1 atm. So if a standard, it had to be 1 atm. So it's not 1 atm, it's 0.1. The next pressure, P of O2, is 0.1 atm. P of NO2 is 2 atm. Okay, So you have these three conditions here, and I'll write out the equation for you. Delta G equals to delta G naught plus RT ln Q. All right, so we have this here. I actually put these equations on your periodic table, so when you check your practice test, you should be able to see these on there on the test. The periodic table should show you, okay? So make sure you double check. When you take your practice test, you see what equations are not on there, and you'll know which one you have to memorize, basically, okay? So delta G equals to delta G naught plus RT ln Q. So we already have delta G naught, we're looking for delta G. So we can go ahead and plug that in here. So this is negative 71.2 kilojoules. But you'll see how plus R, which is 8.314 joules per moles Kelvin. You see how how this now doesn't agree? So that happens all the time. This isn't joules, this isn't kilojoules. So I like to go ahead and just change this to joules because it's easier to just say times 1,000. Okay, now it matches the unit. Okay, R and then T is 298 Kelvin, and then ln Q. And you're like, oh, Q? Okay, so we gotta write Q. So how do we write Q? We have to write the K expression, and Q is the same formula, but you put these numbers in. So let's go ahead and write the Q or the K, which is the same formula here, okay? It's what? Products or reactants, remember? So NO2, right? So we'll put a pressure of NO2 on the top. So I'll just put the brackets there. It really should be pressure. And then it's squared because it's to the power of 2 right here. So 2 here, coefficient 2 to the power of 2 up down here. And then on the bottom, we have NO, and we got to square that also times O2 to the power of 1. So then you put these numbers over here. So NO2 is 2, gotta square it. NO is 0.1, square that, and then 0.1 to the power 1. Okay, that gives you Q, and Q ends up being 4.00 times 10 to the power 3. So make sure you guys are able to do this on your calculator. It's very important to be able to do operations like that. So I'm going to go ahead and plug this number down here, right there. Okay, let me rewrite it like with all the correct values again. So delta G can be calculated using negative 71.2 times 1,000 joules, and then plus 8.314 joules per moles Kelvin times 298 Kelvin times ln 4.00 times 10 to the power 3. Okay, and then you get your answer. So since we're in joules here, it'll be in joules per mole. So this one technically has a joules per moles because it's always per moles here. It's per mole of the equation though, okay? So, so over here, you take this number times plus these three together, value multiplied together. So you have to do the natural log first, and then times this, and then you add with this value here, and you get negative 50.7 times 10 to the power 3 joules per moles, which really means is negative 50.7 kilojoules per moles. Okay? So, and then the question is, let me write it in a different color here. Is this reaction more spontaneous or less spontaneous under these conditions when compared to the standard? Compared to standard conditions. Okay, the more negative it is, the more spontaneous. So standard was negative 71.2. Non-standard in this case was negative 50.7. So it's actually less spontaneous because it's less negative. All right, so I'm using joules over here. If you wanted kilojoules, then yes, it would be divided by 1,000. I just chose to multiply this by 1,000 and then convert it down because I don't like to mess with the constants. But you can do that too. But if you do 8.314 10 to the minus 3, do not convert this over to keep this as kilojoules. But R is 8.314 joules per moles Kelvin, okay? So like remember here, I wrote it out. So this value R here is actually provided on a periodic table. That's the number you see. I think they actually give you 8.315 for yours because it's for something. So just use the value on your periodic table, okay? I typically don't like to mess with constants, so I try to manipulate the values that are not constants so I can keep this the same unit. But you can totally divide this by 1,000 and keep this as kilojoule. That works too. But if you do that, don't be converting this to joules, okay? All right, let's do one more question for K. You guys done with this? I'm gonna go ahead and change the page. If you're not, let me know, okay? All right, so last question here that we wanna do is N2O4 gas goes to 2NO2, okay? And these are also gas. So find K for the follow. And this is reversible actually. For the following reaction at 298 Kelvin, is this reaction spontaneous under standard conditions? So obviously we have a relationship between delta G and K, so I'm gonna go ahead and write it out for you here real quick. The equation was delta G naught equals to minus RT ln K. That was from the slide earlier, okay? And then I'm gonna give you some values for you to solve this here. So delta G formation, and then you have in units of kilojoules per moles. So N2O4 is going to be 99.8 kilojoules per moles. And then NO2 is going to be 51.3 kilojoules per moles. Now, so these are the values here that's given. Now from these values here, I can calculate the delta G of the reaction. Okay, so I need to go ahead and do that first because if they're looking for K, that's what we're looking for. Here, I need to be able to solve what delta G is for the reaction. So let's go ahead and do that. So delta G naught of a reaction is from this table here, and it will be products minus reactants. I have 2 moles of NO2, so 2 moles of 51.3. That's my product minus my reactant, which is 1 mole of 99.8. So that gives me positive 2.8 kilojoules. Okay, I like to stick my R as 8.314 joules, remember? So I'm gonna go ahead and convert this to joules, so which is positive 2.8 times 1,000 joules. So let's put that over here. So positive 2.8 times 10 to the power 3, okay? Joules equals to negative R 8.314 joules per moles Kelvin, T 298 Kelvin, and then ln K. So all we have to do is solve for K there, okay? Now, based on this question here, it says, is this reaction spontaneous under standard condition? Is it spontaneous? If it's positive, it is non-spontaneous. We can already tell, okay? I'm gonna go ahead and write it out. Now, based on a non-spontaneous value, if your delta G is positive, your K is going to turn out a certain value. So let me show you the slide that tells you that, but we can actually calculate to get the K. So we're going to look at slide number 64, where they actually say, if you know at equilibrium the delta G reaction is 0, delta G naught therefore equals to minus RTL and K. If your G was positive, which we had a G that was positive, right? So see here, positive. If the reaction is spontaneous in the reverse direction, it really means non-spontaneous as written, okay? Now, if G is positive, your K will be smaller than 1. So that means when you're calculating your K, you make sure it's a smaller than 1 number because you know it's non-spontaneous. Okay, that's a good indication. Or sometimes they give you, if my K is smaller than 1, is this spontaneous or not? Well, you can say if K is smaller than 1, the delta G naught will be positive, so the reaction will be non-spontaneous, or we can say spontaneous in the reverse direction. Okay, now if your K is bigger than 1, delta G will be negative, delta G naught is negative. It will be spontaneous when K equals to 1, delta G naught will be equals to 0. Our reaction is equilibrium under standard conditions. Okay, so keep this in mind here. And then we're going to go back to calculating here. Now, because this is positive, I expect my K to be a smaller than 1 number. If you got a number bigger than 1, then you might have made a math mistake. It's a good way to check yourself. So now we have to work our algebra, okay? Now, so the idea is I want L and K on one side, and all the other guys go to the other side. So I will divide both sides by negative 8.314 joules per moles Kelvin and 298 Kelvin, okay? So what happens here is L and K is over here now. I just write it so you can see it better. A lot of times I write the L and K on this side already. But let's take it slow. Positive 2.8 10 to the power 3 joules. And then we want to divide it by negative 8.314 joules per moles Kelvin. And this is technically joules per moles here of the reaction. And then 298 Kelvin. And then that's it. All right. So put this into something. So I'm going to write L and K over here now. That equals to negative 1.13 because there's a negative sign here, so it's going to be negative. Now, once you know that, to get rid of Ln, you take e to the power of both sides. So K equals e to the power of negative 1.13. And then back to the same thing we used to use our calculator doing. Just get our answer here, and you get 0.323 for your K. And again, it confirms it's less than 1. We can also say this one tells us it's non-spontaneous as well. Okay, so this is the end of chapter 19.